So, welcome to the test review slides for the second lecture set. Again, I want to remind you that these are meant as a supplement to the lectures, the textbook, and the study guide. They are in no way intended to be a covering of everything that's going to be on the test. They're primarily just a set of slides and or summary slides from the lectures that I thought were worth going over a little bit more to help you study. So again, this is not the only thing you should be listening to, and if I don't cover something in these slides, and in no way does that mean it's not going to be on the test. The study guide is the better indicator of that. These are just some key concepts that I thought I'd like to go over with to help you study. So it's just as a quick reminder that when we're making a measure, every item is going to have a response option. And that response option is going to be a type of scale. So if I ask a question, I can ask it in such a way that it has a nominal response, an ordinal response, an interval response, or a ratio response. So a nominal response is, do you drink? Yes or no. That would be a nominal scale. So the question is, do you drink? And the response is either a yes or a no. So in that case, we can assign numbers. Yes is 1, no is 0. But for the most part, we really don't have any ranking there. We're basically just naming the responses. It could be ordinal. Compared to your friends, do you drink the least, the same, or the most? Now again, we have some ranking there now. We have lower, medium, and top, but it's more of an ordinal scale because we, one, don't know how much your friends drink, and also, so the difference between someone that says more than their friends depends completely on their friends. So we have order. We know that if you say more than, that you have more than that trait than your friends that you're around. But the distance between the same as and more than, and the difference between same as and less than, could be very different. So even if it's from people with the same friends, let's say on average your friends all drink 5 drinks a night, and both you and your friend responds more than, but your more than is 6 and their more than is 20. Ordinal scales don't give us the distance between the responses. It just gives us order, hence ordinal scale. Now, if the items you're asking are measured with an outcome, with a response that's either nominal or ordinal, it may be the best logical step to use, but it limits what we can do as far as testing reliability and validity. So the next level of scale is interval. The distance is meaningful. I drink more than my friends. Strongly disagree, neither, agree, strongly agree. Technically, now we've got a scale that the intervals between each response should be approximately the same for whoever's answering it, regardless of their frame of comparison. And once we have that distance being the same, we can now start running, for example, correlations. We can start looking at internal consistency, and that's definitely what we're interested in. The only difference between an interval scale and a ratio scale is ratio adds absolute 0. In other words, it's no longer arbitrary. So an interval scale, like a strongly disagree to a strongly agree scale, we assign numbers 1, 2, 3, 4, 5. But even if we assigned a 0 in there, so sometimes you'll see an interval scale that's -2, -1, 0 for neutral, 1, 2. That 0, though, isn't an absolute 0. It doesn't mean you don't have any of the trait. It's just an arbitrary number assigned to a scale. If you have a ratio scale, 0 actually means 0. So an example of my question for a ratio scale would be, how many drinks do you have in a night? 0 is 0. 1 is 1 drink, 2 is 2 drinks, etc. Most psychological measures are truly more towards ordinal scales, but we treat them as an interval scale. And basically, there's a gray zone here, but I think the best way to think about this is if you have what's often called a Likert or Likert scale. Likert is actually how the name is pronounced, but a lot of people call it Likert. Of a 1 to 5 scale or bigger or more numbers, you're probably safe calling it an interval scale, and most statistical tests can be used. So when we're creating measures, if possible, we want to make sure that the response options to our questions can be responded to with either interval or ratio data. And the other reason that we want interval or ratio data is if we use interval or ratio data, we can now actually start looking for norms, normal curves, and normal distributions. So we can look to see is the information we're gathering from a sample of multiple people kind of breaking down to a symmetrical bell shape. And if it is, that means that we can now create z-scores to compare scores across different groups. We can actually create a mean and standard deviation to summarize what the data looks like. We can use it to create a cut score that's reliable for decision making. And all of this is only possible if we have a normal distribution, a symmetrical and not perfectly symmetrical. The slide says perfectly. It's never going to be perfect. In fact, we have statistical tests to see, is it good enough? But generally, that normal curve allows us to make some pretty big decisions. So for example, once we calculate mean and standard deviation, we know the mean should be the approximate center point of the distribution. Half of the people scored less than this, half of the people scored more than this. And once we have standard deviation, we also know that plus or minus 1 standard deviation from the mean in a normal distribution usually represents just under 70% of the people. We also know that plus or minus 2 standard deviations from the mean is about 95 to 96% of the people. So this gives us a lot of information. So if we know someone is 2 standard deviations above the mean, we know that they're actually scoring better than approximately 97% of the people that took whatever that measure was. None of this is possible if we don't have interval or ratio data, and it's also not possible unless we have a normal curve. So again, we want to make sure that once we've measured something, if we have interval or ratio data, we want to look at the data, make sure it's coming out as a normal distribution, and we also want to make sure that it is not kurtotic. Remember, kurtotic was either too narrow or too wide. So too narrow is leptokurtic, too wide is platykurtic. And also we want to make sure that it isn't skewed, most of the scores being at the very high or very low end. If it's very high end, so everyone scored high but a few people, that's considered a negative skew. So the skew is skewing out, the tail is heading to the smaller scores. And if everyone scored a low score with a single high, that's considered a positive skew. So central tendency, if we have a normal distribution, that means we can now calculate a mean, and that mean is quote-unquote meaningful. And the mean is simply we sum the total of all the scores divided by the number of scores. So if you have 10 people's scores, you would add all 10 of them up, and then you divide by the number 10. This is the mathematical mean. And we can also quickly calculate a standard deviation. In this case, once we have that mean, we take each score minus the mean squared, add them all up, and divide by n minus 1. Once we have that number, we take the square root, and this is actually the standard deviation. Sometimes this equation will just be n and not n minus 1. Both of them are accurate. Both of them can be used. The n minus 1 is basically a slightly more frugal, or basically it's allowing for a little bit more error. So it's a little bit more conservative in estimating the standard deviation. And again, what we want to find is a nice normal distribution with a fairly broad range of standard deviation. We want to see some variance. So there's 2 examples there. Distribution A has an enormous amount of variance, so we're going to see a very large standard deviation. And distribution B to the right has a much smaller distribution, smaller variance. We're going to see a smaller standard deviation. The other thing we can do is once we have a normal distribution, we can also calculate z-scores, and we can do this no matter what the original scale was. So if we have a measure of intelligence that's on a 0 to 200 scale, we have another measure of intelligence that's on a -5 to +5 scale. If we have a measure of intelligence that's on a 0 to 100 scale. It would be hard to compare numbers if someone took all 3 tests to ask, are they getting about the same score in each test? What a z-score does is it converts whatever data we have into standard deviation units. So the z-score equation is right there. We take the score that we're interested in converting minus the mean divided by the standard deviation. And this can also be done for an entire population, in which case we replace mean with the symbol for mu, that's the little u-looking guy, and standard deviation with omega. And this basically is just the mean of the entire population and the standard deviation of the entire population. So my example here actually is from a population because IQ has actually been normed to be on a mean of 100, standard deviation of 15 scale. So if someone had a, let's take Goofy for instance, Goofy has an IQ of 70, So 70 minus the population mean of 100 is 30, divided by the actual standard deviation of the population, 15. So again, the score of 70 minus 100 means negative 30, divided by 15 is negative 2. Goofy has a z-score of negative 2. What that tells us is that Goofy is 2 standard deviations below the mean. If you'll remember back to that distribution chart, that also means that about 97% of people, assuming a normal distribution, are actually scoring higher than poor Goofy. So once we do a z-score transformation, z-scores are always the same no matter what the original scale of measurement was. Mean will now always equal 0, and the standard deviation will always equal 1. We covered a few quick equations, and I just want to hit them again because you may be called upon them to be used in the test. So correction for guessing is simply an equation where we're actually looking at a couple of things. The first thing we need to figure out is just the probability of guessing. And the probability of guessing, basically getting something correct simply through guessing, is 1 divided by k, which is k of the number of answer choices. So if you have a test with 2 choices, true and false, the chance of guessing is 1 divided by 2, or 50%. If you knew nothing about the material and you're taking a true-false test, on average, you'll get half of the questions right. For a standard multiple choice question, which has 4 options, it's 1 divided by 4, 25%. So on a multiple choice test, you can basically guarantee that even if you have no idea of any of the questions, you should still get about a quarter of them, 25%, correct. Now, we also talked about that in some situations we might want to correct for guessing, and we kind of talked about we usually are going to use this technique when we're using a very high stakes test and we're only testing someone once, and we're using a test which has the possibility for guessing. So if I'm giving an employment test to find out if you know key skills that are required to do the job, I probably want to make an adjustment in your raw score that you get on that test for the chances that some of the questions that you got right, you actually got right by guessing. And how this is done is basically by calculating the number of questions you actually got wrong to basically make an adjustment to say, well, if we know you were getting some of them wrong, that means that a small portion of the ones that you got right, you probably got right just because you guessed. So the equation there is RS subscore C is what we're calculating. And then on the equal side is what we actually need the numbers to calculate, since it's the equation. So the raw score is RS with a little 0 after it. So that's where we put the raw score of the person that we're wanting to convert their score from a raw score to a score that's been adjusted for the potential for guessing. W is the number of questions they got wrong, and K is the number of possible responses. So if you're taking a multiple choice test with 4 possible responses, and the raw score was 5, so you got 5 correct, then what we're going to do is run the equation. So at this point, we got 15 wrong, so 5 minus 15 divided by 3. So that equals 0. That basically means that we're not making, our adjustment is that instead of a score of 5, that person gets a score of 0. Now that sounds pretty harsh, but what that means is they took 20 questions, there's a 25% chance that they get questions right by pure guessing, and they only got that number correct. They got 25% correct. So they actually didn't get 25% correct. Just blind luck got them 5 of them. Their real score is 0. If you run a 20 through this equation, you'll find there's no adjustment because none of them were wrong. But if you run an 18 through, that's where you actually find a little bit of an adjustment. You're going to find a slightly lower score to adjust for the fact that if you missed a couple, you probably may have got 1 or so of those questions right that you shouldn't have. Another quick equation we can use is just to determine item difficulty. So once we give out a scale with multiple items to a bunch of people, we can simply get the number of people that got the number correct by the total number that took the test. So if we had 100 questions and everyone got them right, 100 divided by 100, that's 100%, 1.0. That's a very easy question. If 70 people got them correct out of 100, that's 0.7. And that basically is more of a moderately easy question. But if only 5 people got them correct, 5 divided by 100, that's a very difficult question, 0.05. And this is just another way to kind of quantify and look at a test and determine Do I have too many hard questions? Do I have too many easy questions? And this technique is often used just in the designing of the test that you guys end up taking, and in fact, I ended up taking when I was in school as well. Just a quick review of correlation. The big thing I want to remind you is that correlation is when we're comparing two variables that are both interval data or ratio data, and we're getting a coefficient, which is usually R, though sometimes we might call it something different depending on the specific test we're running. But in all cases, that value, that correlation that we're calculating, is going to range from negative 1.0 through 0 to positive 1.0. And again, the sign only indicates the direction of the relationship. The number represents the strength. The larger the number, the stronger the relationship. The closer the number is to 0, the weaker the relationship. Generally speaking, we also want to determine, do we have statistical significance? And once we have that R, if we actually want to know the percentage of times that the two variables are related, we can get the coefficient of determination, which is R squared. And as you've been told over and over again, just a reminder that just because two variables are correlated does not necessarily mean we have a causal relationship where one variable causes the other. It means we can predict one variable from the other. So just a few assumptions. We talked about a lot of assumptions in class, and I'm not going to go over all of them again in this particular review, but I do want to remind you that one of our big assumptions is that there's traits and states. Both of them distinguish people from each other. However, traits are fairly stable and enduring, and therefore when we're measuring traits, it's a lot easier for us to be looking at reliability and validity. If our intention is to measure states, it's a little bit more difficult for us to validate that test. And everything that we're interested in at least psychological testing and measurement, are these constructs. They're informed scientific concepts developed and constructed to describe and explain behavior and differences between people, but they're not something that usually can be physically measured. They have to be measured through either observation of behavior, self-report, or some other secondary source, which is why we need to create these tests and these measures. We also talked about different ways to norm test, and again, we went over a fair amount of them in class, and some of them are definitely on the study guide. I did want to remind you that the idea of percentiles are a common way to do it, and it's basically just using some of the information we've already talked about, such as z-scores, such as normal distributions, to simply assign someone, instead of a raw score, their percentile score. A good example of this is the GRE, the Graduate Record Exam. You get a raw score, but you also get a percentile. And that percentile is the percentage of people that you did better than. So if you get a percentile of 22%, that actually isn't a very good score. That means you did better than 22%, but 88% of people did better than you. If your percentile is a 97, that means you did better than 97% of the people that took the test, and that's a pretty strong and good score.